Hello, Mr. Claudy here. Now that we're comfortable with using trigonometry to solve geometry problems, we're going to start turning our attention to solving trig equations. Before we get there, we need to learn and discuss some tricks that help us deal with the unique nature of the sine, cosine, and tangent functions. That trick is the unit circle and the cast rule. Both things that you've learned, so we'll be doing kind of a long review of what's an entire chapter of work in one of your previous courses. So we define the unit circle. This is the thing that we're going to use to help us understand a lot of trig for different angles. So the unit circle has a center 0, 0 and a circle with a radius 1, and we consider any point on this unit circle. So if you can imagine, we start with this kind of terminal arm and we can rotate it around and we can represent any angle. So there, consider point AB, which lies on the unit circle. It makes this angle with the x-axis. We'll just consider in the first quadrant for now. So this is point P, which has a length of, or has an x-coordinate of A and a y-coordinate of B. If I drop this perpendicular down, well then, this is A, this is my x, and then this is B, my y, and the radius is 1. Okay, so knowing that, with that in mind, let's use our trig ratios. Cos theta, let's start with that. Well, we remember, so TOA, this is adjacent over hypotenuse, so that is equal to A over 1, which is just A. Then we should consider also the sine theta, so that would be opposite over hypotenuse, which is B over 1, which is just B. Finally, we should consider tan theta, so TOA, which is opposite over adjacent, which is B over A. So essentially, we can represent all of our trig ratios using these lengths A and B. In general, the point P actually has coordinates not A, B then. A is actually equal to cos theta, and the B, the y value, is just sine theta. We're going to see in a few minutes how this can help us determine all sorts of things for any angle. But first of all, let's just talk about our, well, first of all, actually, let's just do a little consideration. Consider if theta is equal to 90 degrees. So if this angle is all the way to 90, well, then in that case, A is equal to 0, right? Because there is no x-coordinate. And so therefore A is, so cos 90 degrees is equal to 0, and B is equal, in this case B, the y value is 1, so therefore sine 90, using that formula, sine 90 degrees is equal to 1. So actually you can figure out right off the bat for 90 degrees, you can figure out what cos 90 and sine 90 are. You can actually use this reasoning, as we'll see later, to find any kind of multiple of 90. So we can use similar reasoning to find sine 180 degrees, cos 270 degrees, etc. Okay, so that's just a consideration. Before we get into looking at other angles and angles greater than 90, let's just introduce our first two trig identities. Trig identities are going to be a big part of this chapter coming up. These two, though, are important ones, and we can actually prove them with this concept that we just showed with the unit circle. With this triangle, Pythagorean theorem would state that a squared plus b squared equals 1 squared. Well, we know that a is equal to cos squared, so this is cos theta squared, and then b is equal to sine theta squared is equal to 1. So that gives us our first trig identity. We would write it a little bit differently. Sine squared theta plus cos squared theta is equal to 1. You're going to see that one come up. You've probably seen it before. Note the notation. Sine squared theta is just a nice way of writing sine theta all squared. The other trig identity that you know by now is tan. Remember, tan is equal to opposite over adjacent, b over a, and we know that b is equal to sine theta and a is equal to cos theta. And you've probably seen that before. Tan is equal to sine over cos. These two identities will be coming back again and again, but this is kind of where they come from, the unit circle. So what's neat now is, before we go to angles greater than 90 degrees, let's just practice sketching different angles on the unit circle. So we have, 75 degrees. Well, that one's pretty straightforward. That starts, remember, we always start at the x-axis and we go up. So that's going to bring us maybe somewhere around here. So there's my 75-degree angle. And it says to label it. Well, this coordinate, the coordinates of this point are going to be a, right, which is cos 75, and then sine 75. Okay, now look how we can do other angles that are not just between 0 and 90. Like, that's the great thing about the unit circle. Negative 33, for example. Well, negative 33 means I start the x-axis and I go down, I go backward, I go clockwise. 33 is going to be approximately this angle here, so that's negative 33 degrees. So this point is cos negative 33 sine negative 33. Let's do another one, 255. Whoa, that's a big number. Well, this is 90 degrees, 180 degrees gets me here, 270 is here, so it's somewhere pretty close, it's somewhere here, I think. It's 255. So this is cos 255, sine 255. Finally, let's do one more, 470. Well, that would be one full loop, gets me to 360, plus 90 gets me to 450. Sorry, 450. And then I need another 20 degrees more to get to 470. Something like that. So that's pretty neat. So this is, which one was this? Cos 470, sine 470. It's going to be real messy, but you can do this kind of full loop, loop to loop. Okay, so we see how we can use the unit circle to represent any angle. What we're going to learn now is how we can figure out the value of any angle. I mean, it was easy enough if we were looking at theta equals 90 degrees, but what if we're looking at angles that aren't multiples of 90? Well, the first, we can talk about the sine of these different angles. So in quadrant 1, remember, this is a Cartesian plane. This is positive x, positive y. In quadrant 1, the x and the y are both positive. That means that a is positive and b is positive. Remember, a and b are sine and cos, but this essentially means that, and tan has to be positive too. In quadrant 2, so remember, this is quadrant 1, this is quadrant 2, quadrant 3, and quadrant 4. In quadrant 2, well, the y value is positive, but the x value is negative. So we're going to have cos a is negative, this is positive, and tan, which is a combination of the two, has to be negative. Similarly, quadrant 3, they're both negative, so actually in that case tan is positive. And in quadrant 4, just the y is negative, the a is positive, so this is also negative. Now, instead of making this table every time we do a question involving trig, it's much easier to remember the cast rule, which is what we teach you in grade 10. The cast rule, if you write it out, just make sure you write it out correctly, is a way of remembering which of the trig ratios is is positive. So here A stands for all trig ratios are positive. This is sine is positive, right? And you can see we have that from the table, quadrant 2. Sine is the only one that's positive. In quadrant 3, only tan is positive. So tangent is positive. I guess you'd say only tangent is positive, only sine is positive, and here you'd have only cosine is positive. So that's one way, first of all, how we know the sign of these different trig ratios. And we'll look at, we're going to do some examples coming up. You might have also seen these supplementary angle properties, like sine of theta is equal to sine of 180 minus theta. This, in some ways, is just a fancy way or a confusing way of rewriting the cast rule, right? If you have a sine of an angle, you know it's going to be positive. That's the same as the sine in this quadrant, so it's 180 minus that angle will give you the same trig ratio. Similarly, we have these other ones for cos. So I don't worry about these too much. I tend to focus on the cast rule and related angle method, which we're going to look at on the next page. For a question where you're looking at different angles and trying to figure out the trig ratios for those angles, you're going to sketch the angle on the unit circle. What we do is we drop a perpendicular from the unit arm to the x-axis. We label the related acute angle, and from that we're able to rewrite the trig ratio with the correct magnitude and the correct sign. So let's turn the page and we'll see how this works. So we're going to rewrite the following trig ratios using the cast rule. So what I want to do is rewrite this into something that I can actually solve. So if you want to, I just sketch these usually. So the first thing I told you to do on my instructions there were to sketch the angle. So 113, well, that's more than 90, so it's something like this. Now remember, cast rule, C-A-S-T. Okay. Oh, sorry, before we do that, drop a perpendicular from the unit arm to the closest x-axis. So I'm going to drop a perpendicular from that the unit arm down, or terminal arm, down to the x-axis. Label the related acute angle, the angle between the unit arm and the x-axis. So in order to figure out what this angle is, cos 113, I'm going to study what cos of this angle is. We call it the related angle. My teacher used to call it the acute friend. What's 180 minus 113? It's 67. So essentially what we're going to be looking at, instead of talking about cos 113, we're talking about cos 67. But it's not enough to just write the new magnitude of the related angle. I also have to consider, is cos positive or negative? I have to consider cast rule. Well, sine is the only positive trig ratio in this quadrant, so cos then would be negative. So cos 113 is the same as negative cos 67. There's going to be a lot of applications of this. I mean, just for kind of a basic introduction to this, you know, your calculator can give you some related angle, or it can give you some trig ratios, like it'll know that this is 0.995. Oh, I'm in radian mode. Whew. Cos 113 is negative 0.391. If I type cos 67 and then multiply it by negative 1, I get negative 3907. Same thing. So your calculator knows in some cases how to find the what this ratio is. But we'll see there are questions where we have to use this property. We have to rewrite as using the cast rule as an acute angle. and this is an approximate value. It's found with the calculator. Okay, let's do another one of these. Tan 7 pi by 11. Oh my god, radians. But remember, radians are the thing that we're going to be using more and more going forward, so I hope you like them. Okay, well, let's start with the angle. Let's draw it. 7 pi by 11. Well, 11 out of 11 would be somewhere here. So 7 pi over 11 would be somewhere here, I guess. So that would be an angle of 7 pi by 11. So what is this? Remember, then I drop a perpendicular. What is the related angle, or what's the acute friend? Well, it would be 4 pi over 11. Hopefully you're good with your fractions. So now I can rewrite this as tan 7 pi over 11. But we got to consider cast rule, C-A-S-T. Well, the sign is positive here, so tan has to be negative. Again, if I change the mode in my calculator, I can take 7 times shift pi divided by 11, tan of that answer, and I get negative, but then I take the negative of that, so it becomes positive. Oops, sorry, I wrote this wrong. Should be 4 pi over 11. 4 times shift pi divided by 11, tan of that answer, gives me negative 2.18, but then it would be the positive, but then it would be the negative of that. So I'd get approximately equal to negative 2.190. And remember rad mode on the calculator. Okay, let's keep going. Sine 1. Oh, what is that? Sine 1. Well, I'm going to sketch this. This is an important thing to note here. If no degrees, if there is no degrees sign, assume radians. In fact, you should just always assume radians. So what is a sine of, or what does 1 radian look like? Well, remember, pi radians is 180 degrees. Pi is 3.14. So 3.14 radians is half a circle. So this is about 1.5. So 1 radian is somewhere here. If you remember from the radian lesson, it's about 57 degrees. So that would be 1 rad. That's about it. There is the acute angle is the same, like there's no change here. You can type it into your calculator if you really want. Sine 1, 0.841. That's just kind of just to remind us how radians can be weird. Okay, so let's look at now some applications where we don't have a calculator. Find the exact value for the following trig ratios. So someone asks you, what's cos 135? You say, well, I have no idea. I don't know. Well, can I write it in terms of an acute angle? Can I use my cast rule and my related angle strategy? So I'm going to draw first, do a little quick sketch. 135 is 90 degrees plus 45. So it would be this angle like this. I drop the perpendicular and I label the acute friend, or the acute related acute angle, which is 45 degrees. So now I can rewrite this as cos 45 degrees. But I'm not done. I also have to consider cast rule, C-A-S-T. By this point, we're used to this quadrant. Cos is negative here. Now, do you know what cos 45 is? Well, you sure do, because that's one of our special triangles. And it's assumed in IB that you know what this is. Now, if you can't remember the trig ratios for cos 45, you can always quickly draw that sign, that special triangle. Remember, the one for 45 degrees is easy. You draw a 90-degree triangle. That's isosceles. Both sides have a length of 1. This is this angle has to be 45 degrees, and this angle has to be 45 degrees, so that they add up to 180. This is root 2, using Pythagorean theorem. So now I know that cos 45 is adjacent, so 1 over hypotenuse root 2, and there's a negative in front, so it's negative 1 over root 2. Oh, imagine you put the special triangle over here. That would have been a better use of space. Okay, let's do sine 7 pi by 6. So again, I'm going to do cast rule. Okay, so pi by 6 would be all the way to here, right? The 6 over 6 would be 1 pi. And then that's an extra pi by 6. So it's somewhere here. So this angle is 7 pi by 6. Drop a perpendicular to the closest x-axis. And the related acute friend is right here. Well, this is going to be pi by 6, aka 30 degrees. But we're looking in a radians world now. So do you remember what, so I can rewrite this as sine pi by 6. Now, cast rule, we have to consider tangent is positive here, so sine is negative. Now, do you remember what sine of pi by 6 is? Or, yeah, sine of pi by 6? Not really, but you can use your special triangle. This special triangle is an easy one to remember too. It starts with an equilateral triangle, which means that oops, I should not write 60, I should write pi by 6. It means that all angles are the same. This is length 2, this is length 2. If you can remember that, then it's very easy to find the special triangle. You cut this triangle in half, now you have a length of 1. This angle becomes pi by 3, or sorry, pi by, I screwed this up. I'm not very good with my radians either. This is pi by 3, this is pi by 3, this is pi by 3, but now pi by 6. Okay, and so now if you want to know what sine pi by 6 is, you would start with pi by 6. You'd look opposite 1 over hypotenuse, which is 2. So you'd have negative 1 over 2. So you can see how you can figure this, the trig ratio out for a lot of these special angles without using a calculator. Another type of question that you might get in IB is like, well, let's say it's a non-calculated question. They would say, okay, we're going to tell you that sine 43 is equal to 0.62. Can you find for us then what sine 223 is? So it's not a special triangle this time, but it is a, it's not a special triangle, but they've given you enough information to figure out what this is. We're going to start do exactly what we did last time. I'm going to draw a diagram, unit circle diagram. And I'm going to draw that angle 43, so that's somewhere here. Okay, now I want to know what sine 223 is. Well, 180 would be here, 223, let's draw in a different color. That's going to be somewhere here. You can kind of see that. 223. Drop a perpendicular. So the acute friend is actually 43 degrees here. So I can rewrite this question as sine 43, but then remember cast rule, C-A-S-T. The sign is negative here. So sine 223 is actually negative sine 43. Sine 43 is 0.62, so this becomes negative 0.682. Similarly, what about sine negative 43? Well, let's draw that down here. So negative 43 goes down here. If I drop a perpendicular here, then this angle actually becomes sine 43. The acute angle is 43. Sine is negative. So again, I get negative 0.682. You get a sense that there are, if you can imagine this 43, this terminal arm 43, being, as it gets rotated around each time, you get each revolution, you get 4 new angles that are all, that you can all figure out the trig ratio for. In this case, these two are negative, but if there's also an angle here, which is whatever, 180 minus 43, so 137, that would be the same as this. Okay, what about cos 43? This is unfortunate because I don't know what cos 43 is. I only know sine 43. However, I do know that sine 43 and cos 43 are related. I use that first trig ratio, or that first trig identity. Sine squared theta plus cos squared theta is equal to 1. Well, sine squared 43 plus cos squared 43 is equal to 1. Now remember, sine squared 43, that really means take sine 43 and square it all, so it's 0.86 or 682 all squared plus cos squared 43, this should be 43 degrees technically, is equal to 1. So I end up with cos squared 43 degrees is equal to 1 minus 0.682 squared. 1 minus 0.682 squared. That gives me cos squared 43 degrees is equal to 0.5348. Now, if you take the square root of that, remember this is technically this whole thing squared. To take the square root of that, you end up with two answers. Cos 43 degrees is equal to root answer plus or minus 0.731352. And what was the question asking? Cos 43. Well, let's look at my answer. Cos 43 has to be in the in this quadrant, so therefore I have to take the positive answer. So therefore, cos 43 degrees is equal to 0.731. I'll just make a note of that. So just a note about that. Cool. Last question that we'll do is an odd radian question. Find two angles with the same tangent as 5.47. So we get a question like this. It is always useful to draw a sketch to help us understand what the question is asking, and to help understand kind of these odd sinusoidal or periodic functions. So we have 5.47. So what angle is that? Well, we know it's in radians. Well, think about it for a second. Think. Half a revolution is equal to pi rads. That is 3.14 rads. This is a good way of helping us understand radians. So all the way around is pi rads, so that's 3.14. If I go all the way around a full circle, that's 2 pi radians. Which is 2 times pi, which is 6.28 rads. So if someone's asking you, hey, tell me about 5.47 radians, well, that's going to be almost at 6 rads. So it's almost going to be a full revolution. So it's going to be something like out here. Oops. So let's draw that. That 5.47. Okay. And what's the question asking? Find two angles with the same tangent as 5.47. Well, if you think about it, tan 5.47, this is cast rule, C-A-S-T, tangent is negative. This is a thing. I'm going to put this off to the side here. Okay, so I need to find two angles that are negative, that give me where tan is negative. Well, tan can be negative in, it's positive here, it's positive here, so it's only negative in this quadrant. So there's, what I need to do is draw the terminal arm in this quadrant. Now there is a little bit of a kind of, the angles are similar, right? Like they're, instead of going, It's almost like it's a straight line if you were to draw it this way. So what is this angle? Because the tan of this angle is also going to be negative. Well, I can figure that out because the related acute angle here, or the acute friend, is 2 pi minus 5.47. I can type that into my calculator just to figure it out. 2 times shift pi minus 5.47. So this related acute friend is 0.813. So then this angle here would also be 0.813. That's my related acute friend. So then this angle has to be full angle pi minus 0.813. And that gives me 2.328. So you have a few options now. You could anytime you want to talk about times when you have the tan of this angle is negative. Well, you could have tan then of 2.33, because then that's going to put the terminal arm in here, the same related angle, and tan is negative here. I can't do tan of 0.813 because then tan will be positive. What's another option? Well, another option would be, I guess, to go all the way around and then some. So it would be to do a full revolution plus 2.3, or I could actually go negative. So tan negative 0.813 will also give me a negative tangent because now I'm in this quadrant again. So if you think about it, and I could keep doing this forever, like there are an infinite number of ways I can represent tan 5.7, right? I could do 1.5 revolutions, I could do 5.5 revolutions, and all the time I'm getting that I'm landing on that position which has the same value as tan 5.47. Okay, hopefully that gives you jogs some memories and gives you some guidance about how to work through the unit circle using cast rule. Your homework for this section is page 451, number 2, 6AC, 7AC, page 453, number 1 to 4. Those are kind of the IB style questions, plus the homework page, and I wrote every other. The homework page should be attached, and there you have. These are just kind of some rote questions just to get really comfortable with this, with the related angles. Remember, related angles are part of IB. They have to be known, and you have to be fast and comfortable with them. So this will get you fast and comfortable with them. You don't have to do them all. I'd say do every other one, and especially focus on the radians because that's the thing you're most uncomfortable with. Good luck with that, and we will see you next time.